Thank you. Well, thank you very much for the invitation. It's great to be here. I guess of all the speakers up to now, I'm the first academic grandchild of Joe, in the sense that I worked with George Papageorgiou as a postdoc, who was Joe's student at NYU before Joe moved to Stanford. So what I'm going to talk to you about is some work. It's kind of old work. In fact, last time I gave this talk, it was on transparencies, and I was looking through them the other day. My 12-year-old daughter was there, and she picked it up and did this, and she said, "Wow, that's so cool." She's never seen anything like that before. So I spent 3 or 4 days transcribing it so that I can show it to you this way. And I was fortunate enough to talk with Joe extensively about these problems, because he had worked on bubbles in inviscid fluids, and this is exactly the opposite spectrum of that, problems of chemical engineering applications where the fluids are very viscous. And he actually wrote a paper, and I will tell you a little bit about it. So the applications are in chemical engineering, where you create huge numbers of bubbles, clouds of bubbles, that you want to use to purify things or do reactions and so forth. And what are the important or difficult things? The difficulties that one encounters is that these bubbles or drops are really quite small, but what happens is you want to use them for mass transfer. And for the experts in the audience, if you look at solute boundary layers on a no-slip surface and a slip surface, so the solute boundary layer thickness will be very different. For a slip surface, it's Peclet to the -1/2 instead of Peclet to the -1/3. Therefore, that affects the transfer rates, and experimentally you can see orders of magnitude reduction. So it's very important to understand when this happens. And in addition to this, and I'll show you experimental and computational results, once you get rigid type behavior, you get wakes forming as well. And wakes are also have a very adverse behavior as far as mass transfer goes. So what's the reason? Well, the reason is that there are surface active agents, surfactants that you may put there on purpose, or if you don't do anything, they're there as impurities. And they get onto the surface and they affect the rigidity of the surface, and I will describe that. But before doing that, let me just give you a general physical context. This is a picture taken with my iPhone from Clift, Grace, and Weber, which is a fantastic book if you want to learn about droplets and bubbles. He was in Cambridge, in fact, in chemical engineering, Clift. What I want to do is, this is just a phase diagram of bond number, essentially. So that's how strong gravity is, versus Reynolds number, how strong inertia is. And I will be operating in this region. Okay, because the bubbles or droplets are small and they're spherical, and if they're spherical, it's easier to do analysis and numerics as well. But in principle, we can do the deformable case also. So here are two solutions that are classical, and we know for solid particles. So think of a solid sphere settling under gravity, or a droplet, which is lighter than water, let's say. It could be heavier than water, either settling or rising. And there are two solutions, two exact solutions that will give us, we can write down solutions of the Stokes equations, and we get, if we work out the terminal velocity for a settling solid sphere, this is what we get. The important thing is just to note the 2 9s there, okay? Everything else is the same in the two cases. Or if you have, so the difference between these two is that this has no slip, this one has perfect slip. And in this case, in the second case, the terminal velocity is given by the Hadamard-Ripchitsky velocity. That's an exact solution of the Stokes equations for a spherical bubble or droplet. And the only difference is that now we get 2/3 and then this factor that involves the ratio of viscosities. So if I have a gas bubble, then the terminal velocity is 3/2 times the previous one. So an increase in the velocity, therefore, in the various things you want to do. So the question is what happens? What happens if you do experiments with these things? You purify water and you put bubbles there and you let them rise. What do you observe? Well, what you observe is that typically they don't look as if they're rising with the terminal velocity of a clean bubble. Instead, I'll show you pictures of it. Instead, they have velocities that range in between the two, between the solid and the free slip one. You can ignore this, actually. I just put it there because of some experiments I'm going to show. The reason is that there are surfactants, there are trace amounts of surfactants in the system, and they go and attract onto the interface. I'll show you a picture. They get convected and kinetically go onto the interface, and they affect the surface tension, and that affects the terminal velocity. So this is the kind of problem I want to show you, and I'm going to show you a couple of possibly surprising results about it. So here's some experimental evidence that gas bubbles in an experiment will not rise according to the Hadamard-Ripchitsky velocity. This is a picture of a water droplet settling through castor oil. The top picture is a clean situation, so we can see that the vortex is symmetric. There's a symmetry about the equator, whereas in this case there are impurities and the vortex gets pushed down. So in fact what happens is that the interface is beginning to get rigidified at the back. That's the reason. Possibly a much more convincing experiment is this by Belfdila and Duineveld from the Netherlands, where they measured the drag on these bubbles, and they compared it with the solid line. The solid line is actually the correlation I wrote down there for solid spheres. Okay, so if you compare it with solid spheres, they're exactly on the solid sphere curve. So these bubbles are really behaving as if they were solid particles. So the reason, so the question is why, and what can we do about it? The why is due to surfactants that are present. Chemical engineers draw surfactants like this with a little blob and a tail, and the reason is that the head is hydrophobic. So, the head is hydrophilic, the tail is hydrophobic, and it wants to go get away from the liquid. So they get attracted to the interface, but they get convected towards the interface by the flow. And then they absorb and possibly desorb and get swept to the back. Now, once they get swept to the back, there's more of them there than there, as shown in this diagram. And the surface tension is a decreasing function of surfactant concentration. Therefore, the surface tension here is smaller than there. Therefore, there's going to be a force going up that opposes the flow, and that's what's causing the rigidification. Now, the experiments I showed before, this is called the stagnant cap. In the experiments I showed before, the stagnant cap takes on the whole surface. Okay, and let me skip this actually. So what I want to do, okay, what I want to do is show you, so experiments show that if you put surfactants in, they will rigidify the surface. What I'm going to show you is some computations that we did that say that if you put the right type of surfactant and you keep increasing the surfactant concentration, you can make the rigidity disappear, and the surface will become mobile and goes as if it's a clean bubble again. So here's the mathematical model. What we need to do, it's kind of complicated, but let me go through it. Navier-Stokes equations in the bulk, but then I also have a concentration of surfactant, C, I'll call it C, and then this gets close to the surface, and then there's a Langmuir kinetic exchange with the surface, where this surfactant jumps onto the surface, and there's a surface concentration now, which I will call gamma, and then the gamma affects the surface tension. Okay, so that's really the mechanism. So what are the equations? Here they are, Navier-Stokes, as we said, with a convection diffusion equation. There's a Reynolds number, a Peckley number, and now let's go through the complicated boundary conditions. So think of those as solved. The boundary conditions are a tangential stress balance that now, because of the presence of surfactants, there is a Marangoni force. And this is the Marangoni force, the derivative of the surface tension with respect to theta, because we're axisymmetric. Now, this of course, is a function of gamma. There's an equation of state that tells me what the surface tension is if I know gamma, which is the local surfactant concentration. And then there are two more equations. There's another equation that tells me that when the surfactants get close to the surface, okay, the C field, when surfactants get close to the surface, then there's a kinetic flux of surfactants with an adsorption and a desorption rate constant. So they can go on and off at a certain rate. If I non-dimensionalize that equation, this is what I get, and this I can think of this as a boundary condition for the C problem. Okay, so this is a mixed boundary condition for the C problem. And then I also need to have a conservation of surfactants on the surface. So this is a convection equation on the surface with a flux of surfactants coming in. So I can equate this to this if I wish. Okay, so when do I get solid behavior? Solid-like behavior will happen when either this number, BI, the Biot number, is small, or this number is small. Okay, and those have a physical meaning, which I can tell you next. Those are the ratio of the diffusive rate to the convective rate. So if the diffusive rate is very small compared to the convective rate, then we will rigidify. And also if the kinetic desorption is small compared to the convection, again, we will rigidify. Okay, so since I'm running out of time, let me tell you what the idea is, and I'll show you some results. So the idea is that if you can find surfactants with large Biot numbers, right, so very, very fast kinetics compared to convection, so they can go on and off very quickly, in particular infinite, say, then mathematically I can solve for the gamma in terms of the C, and study what happens as this parameter varies. So physically all we're doing, we're allowing surfactants to get on and off very quickly. Okay, so what will happen as I increase the surfactant concentration, which is K in my particular non-dimensionalization. Okay, so let me show you some computational results. These are zero Reynolds numbers, just for illustration, really, and then I'll move on to the Navier-Stokes computations. So what's shown here is the drag versus K. K is, think of K as how much surfactant you put into the system. And as I increase K, the drag increases. And if this became completely rigid, it would go up to the drag of 6 in the non-dimensional way I've got it, which is for a solid particle. But what happens is that as you keep increasing, the surface becomes non-rigid. In fact, the surfactant concentration becomes uniform, and therefore the Marangoni force disappears, and we get this kind of result that says that if you have enough surfactant, it will remobilize. And I can see that here, as I keep increasing the surfactant concentration, the concentration is uniform, therefore the Marangoni force, which is its gradient, is going to 0. So a similar thing will happen for inertial flows, and in particular, what I want to do is consider Reynolds numbers which are large enough so that a solid particle would give wake formation. So, so for a Reynolds number above 12, based on the radius, you do get formation of wakes. And what I want to do is fix a Reynolds number where a wake would have formed if it was solid, and then increase the surfactant concentration to show that we do get wakes in this case also. And then we'll see if we can get rid of the wakes. Okay, in the interest of time, let me not show that. So what I'm showing here is computations for a Keller number equal to 100, with Reynolds numbers increasing from 0.5 to 55, and this is for a bubble, right? So as I increase the Reynolds number, we get wake formation, and the wake keeps growing. So if I keep increasing, it will keep going. Okay, so the reason this is forming is because there are surfactants, and there is a partial immobilization of the surface. Now, if we fix the Reynolds number to a value of 50, and again consider two different cases, two different Keller numbers, what I want to show now is that I can use the increase in surfactant concentration to get rid of the wake, and that's seen from both of these pictures. Right? So if I start with the top one at k equals 5, then as I keep increasing the surfactant concentration, I get a uniform distribution of surfactant, and the Marangoni force disappears. Now, there's one big open question. Okay, what the model I presented it says that it's quite easy to find surfactants that would do this, and the reality is that it's not. It's quite hard. In fact, what typically happens in experiments, this is an experiment by a PhD student at City College in New York, what you see is that you do get remobilization. In other words, there's a decrease in the drag, but this happens above the critical micelle concentration, where there is a phase transition now, where surfactants are clumping together. So this leads to quite an interesting problem, where you have to track regions of phase transitioned surfactant with monomer. And that's something we're thinking of doing. So the paper I wanted to mention that Joe wrote on this, after we talked about these problems for many times, he actually took all the theories he developed for artificial boundary conditions for the Helmholtz equation, and applied it to Stokes flow, to slow viscous flow. Now, you may say, okay, well, there's no point doing that because we have an exact solution anyway, but it could be quite relevant, well, could be, I'm pretty sure it's very relevant to both stagnant cap type solutions, where you've got a mixed boundary condition of one piece being solid, the other one not, and also hybrid type algorithms with high Keller numbers. So thank you, and I'll stop there.
Thank you very much, Demetrios. I'm afraid you've run us out of time.
Okay, yeah.